Today we're going to see section 5.7, the inverse of a function. Remember, we're going to have the objective of today is I can explain what an inverse function is or are. I can find inverses of linear and nonlinear functions. I can determine whether a pair of functions are inverses. And then we're going to do some applications. So let's explore a little bit about inverse functions. Consider each pair of functions, f and g below. For each pair, create an input-output table of values for each function. Use the outputs of f as the inputs of g. What do we notice about the relationship between the equations f and g? So what I'm going to start is just creating a table. Okay, I have a linear function in example 1. So I'm going to do, in this case, this is my fx. Okay. I'm going to have my input is x, output is y. I'm going to start with 0. Okay, it's just a small table of value. 1, 2, 3, and 4. So if 0 times 4 is 0 plus 3 is 3. And if I continue that way, they are going to have 1. 4 times 1 is 4 plus 1 is 7. Then if I have x equals to 2, I'm going to have that y is equals to 11. And then I have 15 and finally 19. So that's my table of f of x. Now I'm going to create my gx table. And remember that the instruction says, well, I'm going to do the table here. I just screw up this one, x and y. It says that create an input-output table value for each function. Use the output of f as the inputs of g. So in this case, my inputs are going to start with 3, 7, 11, 15, and 19. And we plug in the gx. 3 minus 3 is 0. 0 divided by 4 is 0. Okay? Now 7. 7 minus 3 is 4. Divided by 4 is 1. Can we see the pattern now? We're just reversing the operation. 11 minus 3 is 8. Divided by 4 is 2. And we're going to have 15 divided by 15 minus 3 is 12. Divided by 4 is 3. And then finally, definitely, we're going to have 19, which is going to be 4. Okay, now let's do the second part. I have my fx table, and for this one I'm going to be careful with my inputs and my outputs. Why? Because I don't want too big of numbers for this example. I'm going to start for this one again with the easiest number of all is 0. Then I'm going to have 1, 2, 3, and 4. It's for the square root function that I'm going to be very careful with my numbers. I don't want to put negative numbers there. So 0 to the third power is 0 plus 1 is 1. And then 1 to the third power is 1 plus 1 is 2. Then I have 2 to the third power is 8 plus 1 is 9. And so on. I'm going to have 28 and 65. Okay. Now I'm going to do my gx. Okay. So x, y, and remember that my outputs are going to be the inputs. So 1, 2, 9, 28, and 65. And we're going to do 1 minus 1 is 0. Cube root of 0 is 0. Now I have 2. 2 minus 1 is 1. Cube root of 1 is 1. Can we see we are getting the same values? Now I go with 9. 9 minus 1 is 8. Cube root of 8 is 2. So 28, in this case, 28 minus 1 is 27. Cube root is 3. And then I have finally 65 is going to be 4. Okay, I have now the same values on the other side. Now I'm going to the third part, is fx. I'm going to have fx. I have inputs, output. I'm going to write my tables. I'm not going to have negative numbers here. And this one is, I have an x minus 3. So I'm going to start with the value that makes my table equals to 0. So I'm going to start with 3. Because 3 minus 3, 0 square root of 3 is equals to, in this case, 0. Now, I'm not going to do 4 because it's going to give me a value that is not a perfect square. I'm going to look for perfect squares, so I'm going to use 7, okay? Because 7 minus 3 is 4, square root of 4 is 2. And then I'm going to use, in this case, 12. I'm going to use 19, and I'm going to use 28. Okay, and if we plug in those numbers to save time, in this case, I'm going to have 0, 2, 3, 4, and 5. Now I'm going to do my gx. So I have x, y, and I'm going to use 0, 2, 3, 4, 5. And I'm going to get, as a result, 0 to the second power is 0, plus 3 is 3. 2 to the second power is 4, plus 3 is 7, and so on. I'm going to have 12, 19, and 28. Now, in this case, what do you notice about the relationship between the equations f and g? They are inverses. They are inverses. Okay. Now, b, what do you notice about the graph? In this case, of each pair of functions in part A. So I'm going to write a sentence here. The graph of G, I'm going to put is a reflection in the line y equals to x of the graph of f. Okay, now how do I get to that conclusion? I'm going to graph. Okay, I'm not going to spend 20 minutes on graphing, so I already graph it, and I'm going to show it to you what's happening. So I'm going to do the first graph. Okay, the first one, I have fx is equals to 4x plus 3, which is this function here. So that's my straight line. Then I have the gx. So I have gx, and this one is my y equals to x. And as we can see, this line reflects on my y equals to x line. So it's going to be a reflection on those lines. Okay, see how it looks? It's just like moving this one over here, reflected by the y-axis. Look at this one. I have this point, and you're going to have this same distance from here to here, and you can just do it here to here, and you can just pick another one like this one here, and just reflects same distance here, here. See? Now, the second example is the x cubed. So I have this one, okay? So this is my cube function, as we can see, the blue one. Then I have my y equals to x is the green line, and it's reflected on this line, and I have my gx, in this case, here. So we can see those ones pretty neat, how they reflect each other. You can just follow these lines and see. Use Desmos and play with those graphs. The final one is the one that we need to be careful. Remember that in this case, the quadratic function, I'm going to get a quadratic function, but my original function is fx is square root of x minus 3. We cannot use negative numbers. That is why I'm restricting my gx, because my original function fx starts from, this case, positive 3 and goes to positive infinity. There is no graph on the negative side of the y. So in this case, when I reflect these values, my gx, the inverse, is going to be x squared plus 3. Now I'm going to restrict this parabola to x greater than or equals to 0. So I don't have negative values on my x, okay? Remember that in the previous lesson, the domain of the composite function was affected also by the domain of the original function. So that's what's happening in this lesson also. Okay, so for C, what we have, for each pair of functions in part A, find the composite f of g of x and g of fx. What do you notice? Okay, so I'm going to do what we did in the previous lesson. So I have f of gx. Okay, I'm going to do the first one, and this is equals to f of x minus 3 over 4. So what is this one? So I have 4 of x minus 3 over 4 plus, in this case, 3. What happens to these 4s? This cancels out. Okay, so what I have left is x minus 3 plus 3. And negative 3 plus 3 is 0, so I have that x. So my composite function, f of gx, is equals to x, which is the reflecting line. So this indicates that they are inverse function. And if we do also, in this case, g of fx, okay, what are we going to get? So I have, this is equals to g of the function of x, 4x plus 3. So it's equals to 4x plus 3 minus 3 over 4. 3 minus 3 is 0. So what I have left is 4x over 4. 4 divided by 4 is 1. So g composite of fx is equals to x. Okay? So that indicates that they are inverse functions.